हेलो बच्चों, तो आज की क्लास हमारी है हाइब्रिडाइजेशन। इन दिस चैप्टर वी आर गोइंग टू स्टडी अबाउट हाइब्रिडाइजेशन, टाइप्स ऑफ हाइब्रिडाइजेशन, एंड आफ्टर दैट ज्योमेट्री ऑफ पर्टिकुलर मॉलिक्यूल्स. After that, we will also study about the applications of hybridization. So, as all of us know, these are the shapes of S, P, and D orbitals, and this is the introduction of hybridization. Now, coming to what is hybridization? Firstly, we will answer one question, that why we need hybridization. Because if we don't need anything, we will not do that thing. Okay? तो इसकी क्या ज़रूरत पड़ी, पहले हम इस एग्जाम्पल पे चलते हैं. यहाँ पर आप देख रहे हैं जो स्ट्रक्चर, दैट इज़ ऑफ BeCl2. Here beryllium is having two orbitals for the bond formation. Okay, that is, one is S and one is P, and chlorine have the P orbital available for the bond formation. But when we see this compound and the bond length, this is same in both the side. It means that if these two orbitals are coming together to make a bond, okay, there will be 1s 1p and there will be pp, so there must be some difference in the bond length, but this is not the case. So here it means that they are not participating in the bond formation like this. Okay, so from here we get to know that when we experimentally see the values of the bond length, we find out that this bond length and this bond length was equal. It means that whatever the characteristic this bond length is having, this bond is also having. Okay, so from here this hybridization thing started. यहाँ से हमने ये सोचना शुरू किया कि ये ऐसा हुआ क्यों. ठीक है, तो आप यहाँ पे देख रहे हैं जो s ऑर्बिटल था B का, that started intermixing, which means intermixing of orbital means hybridization. Okay, their orbitals which are intermixing should be of almost equivalent energy so that they can perform the hybridization. Now this is the p orbital, and after hybridization these are the products which we get. It means that the products are similar and these products are similar, so the bonds are similar on both of the side. So these are not participating in the bond formation here, these are participating. It means hybridization took place while the formation of the bonds. Okay, now coming to hybridization's introduction. This was the topic introduced by Pauling. This is very important. Okay, according to him, atomic orbitals combine to form new set of equivalent orbitals known as hybrid orbitals. So if, as we have discussed in the previous example, if one s orbital and one p orbital are coming together and they are intermixing and forming equivalent orbitals, the number of orbitals participating and the number of orbitals we will get as hybrid orbitals will be the same. So if 1s and 1p is coming together to form hybrid orbitals, there will be 2 sp orbitals. Why 2? Because this was 1, this was 1, and since hybridization, after hybridization we are calling it sp orbital, and since they were 2 in number in the starting, in the end they should be 2. So this is what, which is very important, which should be in our notice. Coming to the next thing, the process, the particular definition of hybridization is, it is the process of intermixing of orbitals of slightly different energies. Okay, you cannot mix directly s with d. Okay, you have to see there must be a slight very less difference in the energies of the 2 orbital, 3 orbital, whatever is the number of orbital which are coming together to form hybrid orbitals. So there should be a slight difference in the energies the process of intermixing of the orbitals of slightly different energies so as to redistribute their energy, resulting in the formation of new set of orbitals of equivalent energies and shape is called hybridization. Whatever the orbitals we have taken, while hybridization, what will happen? We will redistribute their energy, and the hybrid orbitals will have the equivalent energy as the previous set of orbitals and the equivalent shape. Okay. Next is, for example, if 1 2s and 3p orbitals of carbon hybridize, there is the formation of how many hybrid orbitals? Obviously 4. Okay, here 1s and 3p are coming together, so the hybrid orbital will be named as sb3. They will be sp3 orbitals, but how many number? 1 plus 3, that is 4 sp3 hybridized orbitals we will get. Okay. Next, there are some important conditions for hybridization. Okay, it's only two atoms coming together and forming a bond. Okay, it is not the essential condition for hybridization. There are many factors which need to be taken care of while this thing happens. So the first point is the orbital present in the valence shell of the atom are hybridized. जैसे हम वैलेंस इलेक्ट्रॉन पढ़ते हैं, तो जो वो वैलेंस इलेक्ट्रॉन जिन सेल्स में है, ओके, दोज cells having orbitals, they will be participating in the hybridization. So orbital presence in the valence shell will participate. Understand the fact that orbitals are participating here in the hybridization, not the electrons. Coming to the second point, the orbitals undergoing hybridization should have almost equal energy. They are not saying that equal energy, almost equal. Okay, if one of the, say if someone is having 4 kilojoule of energy and somebody is having 4.001 kilojoule, okay, it is just a general discussion, so it is not equal, it is almost equal. So like this, the orbitals are not having equal set of energies, they are having slightly different energies, which means almost equal. Come to third point, promotion of electron is not essential condition prior to hybridization. If you are taking, whenever the bond formation takes place, there is promotion of electron from ground state, it goes to the excited state, it happens, but it is not necessary that prior hybridization it should take place. It can take place while hybridization is going on. Okay. Fourth point is, it is not necessary that only half filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. Okay, so it can happen that even filled orbitals are taking part in the hybridization, because the main motto of hybridization is to give a stable structure. Okay, and that can happen with the filled orbitals also. It is not necessary to have half filled orbitals. Yes, there are some features of hybridization which we must keep in mind while we are going through this topic. Okay, the first is the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. This thing we have also studied earlier, that if 1s is coming and 1p is coming, then there will be 2 sp hybrid orbitals. Okay, so number of orbitals participating and the number of hybrid orbitals obtained will be equal. Come to next point, the hybridized orbital are always equivalent in energy and shape. All the hybrid orbitals we will get, they will be equivalent in energy and shape also. Okay, come to next, these the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals, because the hybrid orbitals formed are so in shape, in energy distribution, that they are more effective in forming stable bond. Okay, since we have done in hybridization, what we have done? Yes, in hybridization, what we have done? We have taken the atomic orbitals of slightly different energy and we have redistributed their energy. Okay, and the new set of orbitals was having equivalent energy and almost equivalent shape. So here the shape and energy distribution make them more effective in forming the stable bond in comparison with the pure atomic orbitals which were participating in the hybridization in very starting. Okay, next point, these hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs and thus stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecule. Why we are using hybridization? This question is answered here. What is the application of hybridization? Hybridization gives us a view to tell the geometry of a particular molecule. If we know the hybridization state of a molecule, we can predict the geometry of the molecule and somewhere behavior also. Okay, if we know the geometry, we know the behavior. Okay, if we know the bond angle, we know the behavior. Okay, now see, always the hybrid orbitals are directed, are placed in such a manner that there is minimum repulsion between the electron pairs. Why it is done? Because if there will be minimum repulsion, there will be a stable structure, and that is what we needed. Okay, yes, each hybrid orbital having two lobes, one is larger and one is smaller, and the larger lobe will form the bond. Okay, this I will show you when we will be taking the next example. Come to next, the number of hybrid orbitals on the central atom of a molecule or ion equals to number of sigma bond plus number of lone pair of electrons. See, whenever we are finding the number of hybrid orbitals, what we will do? We will count the number of sigma bonds. Remember, number of sigma bonds, and here we are counting the number of lone pairs, not the lone pair electron, plus number of lone pairs, and after counting these we will be able to tell the number of hybrid orbitals present in a particular molecule. Come to next, one atom can represent many hybridization state. See, there is carbon. Carbon is capable of showing many hybridization state. Okay, it can show sp hybridization state, sp2, sp3, sp4, not sp4. Okay, depending sp3 and many more depending upon the atoms to which it is connected. Okay, so one atom can show more than one hybridization state depending on the molecules attached and the orbitals participated in the hybridization. Come to next point, this is very important. The repulsion between lone pair is maximum. We are talking about a molecule in which if there are two lone pairs present, two bond pair present, and then the lone pair will be maximum. After that, lone pair and bond pair repulsion will be less than that, and bond pair repulsion will be even lesser than both of them. Okay, so this is the order of repulsion between the pair of electrons present. Okay, this is an important thing, this should be remembered. Come to next property, the directional property in hybrid orbital is more than atomic orbitals. The directional property in hybrid orbital is more than pure orbitals. Why? Because if S, we will choose S orbital, its directional properties are less, but when it mixes with p orbital, the directional factor increases. So the orbital which is participating increases the directional property. In comparison with the pure atomic orbitals, hybrid orbitals always have more directional properties. See here p orbitals are increasing, and you are able to see that the less s character is there, more directional property is there. So this is the order for the directional property. Okay, so these are few features of hybridization which we should always remember when we are dealing with this topic. Yes, see, there is one question I have also told you while explaining many things here in the previous slide. By hybridization we mean the mixing of what? Okay, see, atomic orbitals is the answer, but sometimes students get confused with the electrons, because here we have also talked about lone pair and bond pair, so we will not confuse with it. The hybridization is the intermixing of pure atomic orbitals to produce hybrid orbitals of equivalent energy and shape. Okay, yes, see, types of overlapping and nature of covalent bond. Okay, this is little bit we can say out of this topic, but this is the basic which we must know. Okay, when s orbital overlaps s orbital, sigma bond is formed. Okay, here see, this one positive phase is shown by this color and this is negative phase. Okay, this is positive phase, this is positive, this is negative, this is negative. Okay, so when s orbital overlaps with the p orbital, this is head on overlapping. Okay, and the sigma bond is formed. Here also they are having head on, or we can say axial overlapping, and this will also form sigma bond. After this, see, there is one more possibility. This is positive phase, this is negative, positive, negative, you can take any color as positive or negative. Okay, here it is switched. See, here these two orbitals are combining and you are getting this kind of shape. Okay, this shows that this is sidewise overlapping, this is not axial. Okay, this will not form only sigma bond. Okay, there will be a pi bond. Always remember that in one pi bond there is one sigma and one pi bond. Okay, so wherever you find these kind of structure, you will be able to understand which is the sigma bond and which one is the pi bond. This is for that knowledge only we have introduced here. So there are types of hybridization. Okay, when 1s and 1p is participating, sp, here 1s and 2p, then 1s 3p, 1s 3p 1d, there is 1s 3p 2d and 1s 3p 3d. These are the hybridizations we will discuss. Okay, come to this thing. One of the things I have left there, I guess, in the previous slides, that I have told you that we will discuss in the upcoming one. Yes, that was about the I think stable structure. Okay, so we will read about the stable structures here. See, hybridization is find out when there is no lone pair and when there are lone pair. So firstly we will discuss the cases where there is no lone pair present on a molecule, because it will be easier for us to understand that how the geometry of a particular molecule is made when there is no lone pair. Because if you will understand it without lone pair, when the lone pair concept will be introduced, you will be able to understand it properly. Okay, see here 1s and 1p orbital is participating. After this we have told that whenever the hybrid orbitals will be formed, one lobe will be the smaller one and one will be the larger one, and the larger one will take part in the bond formation. This you have to remember. Now coming to it, it is sp hybrid structure. Okay, it is having sp hybridization. Now what are the features of sp hybridization? See, two hybrid orbitals are arranged in a straight line. You can see the straight line, okay, at an angle of 180 degree. Sorry, this is 180 degree. You can see it when there is no lone pair, they are forming a straight line, and this angle is of 180 degree. S character is 50%. Now how to find out the S character when we know the hybridization? See, you can do one thing which is very easy. Here 1s and 1p is participating. It means how many things are there in total? 2. We have to find out the percentage of S character. Okay, how many S are here? 1, and multiply by 100. You will be getting 50%. You will be getting 50%. So this molecule is having 50% S character and 50% P character. Now coming to next example of it, if you will make CO2, C double bond O, C double bond O. Here also I have told you that we will not count it as 2 sigma bond, because one double bond means 1 pi and 1 sigma bond, and while we were talking about the hybrid orbitals, we have only counted sigma bond and the number of lone pairs present. There is no lone pair on it, okay, and the sigma bonds 1 and 2. So since it is having 2 sigma bond, it will have sp hybridization. How come sp? See, 1s 1p, it will become 2. For 2 we will write sp. For 2 what we will write? Sp. So it is sp hybridized. Come to next is sp2 hybridization. Okay, in it what happens? In it we will be having the participation of one s orbital and two p orbitals. You are able to see one s orbital here, it is one p and it is another p. Okay, so here you can see after participation there we got a hybrid structure. Okay, the hybrid structures are given below, you can see. Okay, since there were 3 things participating, we have already understood this fact that the number of participating orbitals and the number of hybrid orbitals will be the same. Okay, so we will get the same number of hybridized orbital but of equivalent shape. So this is what we get. Okay, here the bond angle is 120 degree. And what are the other features? Let's see. In sp2 hybridization, 3 hybrid orbitals are arranged in trigonal planar shape at an angle of 120 degree. Let's have an example of BF3. We will be forming 3 sigma bonds with F. They will be arranged in such a pattern. Okay, let's join them. So this will be the geometry of BF3. Here you can clearly see this angle is 120 degree. Okay, that we can see that these are at equal distance from each other. Okay, adjacent F की बात हो रही है, ठीक है. ऐसा जो adjacent F हैं वो एक दूसरे से एक equal distance पे है, एक same angle पे है, that is 120 degree. Okay, and because of such geometry they are having 120 degree angle each, and here this kind of geometry is called trigonal planar shape. That is called trigonal planar shape. Okay, now here how to calculate the S character for S character calculation, again go to the same method. Okay, what we will do here, we are talking about sp2 hybridization. It means 1s and 2p. Out of them, if we will calculate it, it is 3 number, 1 plus 2, that is 3. How many s are here? 1 multiplied by 100%, and when you will cut these things, there will come 33.3%. that is your S character. Okay, this is how we can calculate. Come to sp3 hybridization. Now what has changed? With each hybridization, what is changing here? See, the number of participating orbitals, and since the number of participating orbitals is changing, the name is changing accordingly, and since the redistribution is changing, we are getting different hybrid orbitals, different number of hybrid orbitals and different equivalent shape, okay, in comparison with the previous cases. Now come here, here is 1s, p, 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 and now how many s orbitals are there? Number, okay, you will not get confused that there is written 2s. We are counting number, how many s orbitals are there, okay. 2s is the name, that is this is 2s orbital, this is 3s orbital, this is 4s orbital, okay. This is the name, we are asking about the number, okay. So 1 s orbital is here, 1 plus 1 plus 1, 3 p are there, 1 s is there. So the name of the hybrid orbitals will be sp3. The name of the hybrid orbital will be sp3 hybrid orbital. Now after combining this, we will get sp3 hybrid orbital, and they will look like this with the bond angle. The structure will look like this with the bond angle 109 degree, 109.28 degree, okay. See here, the 4 hybrid orbitals are arranged in straight line and at an angle of, sorry, not in straight line, okay. Since it is sp3, this is written wrong here, I am correcting it, it is an editing mistake, okay. They will be tetrahedral, okay, they will be tetrahedral. See, I am taking one example. Carbon attached to the 4 hydrogen atoms, each of them is at an angle of 109.28 degree, okay, or we can say 109 degree 28 minutes, okay. So this will be the structure, this will not be the case, okay. Here how you will calculate the structure, sorry, s character, 1 s is present, and how many p's are present? 3p. Total how many orbitals are there? 4. Out of them how many s are there? 1 into 100%, and it will come out as 25%. If somebody asks you the reverse, okay, अगर आपसे रिवर्स पूछा जाता है कि s कैरेक्टर की जगह आप बताइए कि p कैरेक्टर कितना शो करेगा ये स्ट्रक्चर, तो आप कैसे बताएंगे? Either you can do it, you can minus it from 100, it will be 75%, or you can go by the exact long method. There are 3p orbitals, okay, there are 3p orbitals, total number of orbitals 4 into 100, and you will get the same answer. This is how you can do it. See here, there is one case, this is one of the important question which is always asked, okay, that NH3 bond angle is reduced to 107 degree from 109 degree 28 minutes. Why? So that is the case when lone pair is present, okay. And since we have read about the lone pair repulsion, lone pair bond pair repulsion, and bond pair repulsion, we can answer it by using this thing, that this happens because of the lone pair bond pair repulsion, the bond angle decreases, okay. See, this is sp3d hybridization. In this hybridization, there is the entry of d orbital. So sometime the question is asked that which d orbital participates via forming sp3d hybridized state. Okay, in this hybridization, dz square, that is dz square, this d orbital participate. What can be the reason for it? Very simple, because this is having the almost, we can say, almost equal or slightly different energy or equivalent energy with the orbitals which are participating in the sp3 hybridization. Okay, see, in this structure there is one more important thing, that we are taking example of PCl5. In this we have discussed one point, that all the orbitals, all the bonds are arranged in such a way that the molecule attains the stable geometry. It attains the stable geometry, okay, minimum repulsion state. So for that, here two types of bond are present. Okay, but two types of bonds are present: axial bonds and equatorial bonds. There are 3 equatorial bonds and there are 2 axial bonds, and there are 2 axial bonds. See, these bonds, just like equilateral triangle, okay, these bonds are called equatorial bond. There are 3 equatorial bond and there are 2 axial bonds. What is different in these 2 bonds? Okay, here these 2 bonds, 2 axial PCl bonds are longer and these bonds are smaller. Okay, why it is so? Due to the repulsion, between bond pair of electrons. Okay, that's why it attains such a geometry to minimize the repulsion and attain the stable geometry. Now see here, so this happens, this is s orbital, p orbital, p orbital, p orbital, and this is dz square orbital, that is d orbital. They participate in the hybridization and in the end they give such a geometry to the molecule. Okay, so in this case there are 2 axial bonds and there are 3 equatorial bonds. This is the case of PCl5. Coming to sp3d2 hybridization, SF6 shows such a hybridization. Okay, in this what will happen? Just like the other cases, obviously one s orbital will participate, 3 p orbital will participate and 2 d orbital will participate. It means in total we will be having 1 plus 3 plus 2, that is 6 hybrid orbitals. It means 6 bond. You can check here, 1 2 3 4 5 6 bonds. Okay, they will also be arranged like this. Okay, 4 bonds will form a square and 2 bonds will be in the axial position. Okay, this geometry is known by 2 names. Okay, one is symmetrical octahedral and the other one is square bipyramidal. You can see the structure again, it looks like a square. Okay, having 2 pyramidal geometries attached to it, that's why it is named like so. Okay, or the other name you can use, that is symmetrical octahedral. Okay, this is shown by SF6. Angle between all the hybrid orbitals will be 90 degree in such a hybrid structure. So there are some cases we have dealt with, and there is the summary of it. There is a summary of it. See, the first molecule we have we had as an example, that was BeCl2, I guess. Okay, let me check once. Yes, it is hydrogen helium. Okay, so it is BeCl. Okay, then that was a journal structure. We are taking names as journal 1 here. Journal in case that this is the central atom attached to two monovalents. Okay, so here total number of bonds 2, lone pair 0. Structure will be, since it is 2, 1s plus 1b equals to 2. Wherever there is 2 bond pair, no lone pair, sp hybridization will be there, and the shape or geometry will be linear. Example, BeCl2 CO2. Come to next, this is also journal term. Here A is the central atom and B are the monovalents joined to it. So here the bonded pair are 3, lone pair 0. Kindly see that here we are dealing with the cases where lone pair are 0. So the hybridization here is sp2. This will give trigonal planar geometry as we have discussed in BF3. Okay, B was there, F, F, F. That kind of geometry was trigonal planar. After that, for 4 bond pairs, sp3 tetrahedral, and examples are CH4, CCl4. Okay, next is 5, a molecule having general formula AB5, where A is the central atom, B are the monovalents connected to it. Here lone pair 0, hybridization sp3d. It will give trigonal by pyramidal geometry. This is the geometry of PCl5. You have seen 2 axial bonds, okay, and there were Cl in the equatorial position, and this was making the geometry where we can see a trigonal thing with the pyramids attached to it. That's why it is named like trigonal bipyramidal. After that, we were dealing with SF6. SF6 were having 6 orbitals participating. Okay, hybridization sp3d2. It is octahedral in shape, and example is SF6. Okay, if there are 7 orbitals participating, sp3d3 will be the hybridization. Pentagonal bipyramidal will be the name of the shape they will have, and the example is IF7. Okay, come to next thing, methods for determining hybridization state. There are many methods to determine hybridization state, but we use the one which is suitable at that particular point of time. Okay, see here, number of hybrid orbitals equals to number of sigma bond plus number of lone pairs. Since we were not having lone pairs here in the structures we have discussed, so their number of hybrid orbitals was equal to the number of sigma bonds formed. Okay, I have told you that if it is sp, it means 2 hybrid orbitals, 3 hybrid orbitals means sp2. Just like that, we will see the number of sigma bonds and will go on if there are only sigma bonds. But if there are lone pair present, then we will use the whole formula. Come to next, methods for determining hybridization state. Method 2. Okay, number of hybrid orbitals equals to half of valence electron in the central atom. See, this is the half of this whole thing. You will add the valence electron in the central atom, then you will add the number of monovalent atoms connected. After that, charge. How to deal with the charge? If there is something like NH3 or NH4 positive, okay, if there is something like that, if there is positive charge, then you will minus the charge in this formula. If there will be SO4 minus, there will be negative charge, you will add the charge. We will do the reverse. If in the particular ion given there is positive charge present here, we will minus the number of charge from there. If it is SO4, sorry, if there is SO4 2 negative, now it is correct, okay. So whatever the charge is here, if it is having minus sign, what you will do, you will write +2 there, okay. This is how we will do the things. This is how you will do the things, okay. So what will you do? You will see first. What thing you will see first? You will see here, the valence electron present in a particular central atom. Then you will add number of monovalent connected to it. Then you will plus minus charge accordingly, whatever is the charge present there. Now let's discuss some structures we have studied which are also present in your NCERT, okay. See, if there are number of electron pairs 2, both of them are bonded linear, shape. Examples were BeCl2 and HgCl2. Again, if there are bonded, we are talking about bonded electron pairs because we are dealing with the molecules which are not having lone pair right now, okay. See, after that 3, this will be the example BF3, the structure will be trigonal planar. See, whenever there is no lone pair present, the geometry and shape is similar, okay. But when we will go to the lone pair present, we have a difference in it. Now come to next for 4, tetrahedral. CH4 is the example. See here NH4 positive is written. NH4 positive is having 4 bonded monovalent. See here, if NH4 positive is written, it means that, see, what is the atomic number of nitrogen? It is 7, okay. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. It is 7. 2, 5, it means it is having 5 electrons, okay. There is positive charge, it means it has lost 1 electron. It means 1 electron is removed. Now it is having 4 electrons, and since there are 4H, it means H came with 4 electrons, 1H, 2H, 3H, 4H, okay. It means valencies are satisfied like this, okay. This thing we understood. After this, if they are bonded, how they will be bonded? Obviously like this, positive, okay. So it means it is having 1, 2, 3, 4 sigma bond. It means sp3 hybridization state, okay. We can also do it with the formula number of hybrid orbitals. See how we can calculate. Here, half valence electron in the central atom that are 5 in number, plus number of monovalents, that is 4, okay. Plus minus charge, see, there is plus charge, so we will minus it. This thing done. After that, 9 minus 1, that will be 8. 8 by 2, it will come 4. it means sp3 hybridized orbitals are present in this structure. So this thing you can do by two methods. Either count the number of sigma bonds, okay, and if you are finding difficulty to do it in such a way, then go to the formula given and use the formula and do it. So we have done it for NH4 positive. Come to next structure. Next structure is of PCl5. Here it is trigonal bipyramidal. There are two axial bonds and there are three, this one and this one, equatorial bond. Equatorial bonds have an angle of 120 degree. We are talking about equatorial bonds, okay, with each other, and the axial ones are having 90 degree angle with each other. Now coming to octahedral shape, it looks like this. You are able to see here, and SF6 shows the octahedral shape. Here SF6 means SP3D2, 1S, 3P, that is 4, 5, 6. 6 number means this hybridization state, okay. So here we have discussed about the structures which were having only bond pair, not lone pair. We will have a quick view to the structures which are also having lone pair on them. See here, there is given a general formula AB2E. Here E means lone pair, okay. Number of bond pair 2, number of lone pair 1. This is how lone pair is shown here. Arrangement of electron pair says that the geometry of the molecule should be like this. The lone pair bond pair should be arranged in this way, in trigonal planar way. But since this one is not counted in the shape, it shows the bent shape, okay, and this kind of a shape is shown by these structures, okay. Now come to next. Here AB3E is written. It means bond pair 3 and lone pair 1. You can see here, okay. This should be arranged in tetrahedral geometry, but it shows the shape trigonal pyramidal, that is NH3, because N is connected to H, and one lone pair, okay. Now come to next. Here they have given the formula AB3E2. It means, sorry, AB2E2. It means 2 bond pair, 2 lone pair. They should be arranged like this, just like tetrahedral geometry, but the shape is bent shape. This is shown by H2O, that is water. Water makes the geometry like this. O in the center, connected to 2H bond pair electrons, and there is one lone pair and there is another lone pair. So it is somewhere arranged in the tetrahedral geometry, but because of the lone pair repulsion, lone pair bond pair repulsion, it shows the bent shape. Come to next. Here you can see AB4E. This is the general formula given. It means 4 bond pair, 1 lone pair. Lone pair is given this position, okay, and this is the structure similar to PCl5, but there is one difference, that is here lone pair is present. So because of the presence of lone pair, we will not see this while we are discussing the shape. We will cover it with the hand, and now we are able to see the seesaw structure. You have seen a seesaw like this. Here one person sits and other person sits here. So somewhere it is showing such a seesaw structure and there is one lone pair. So while giving the shape, it will show the seesaw shape, while geometry means arrangement will be like this, and shape will be seesaw shape. It is shown by SF4. It is shown by SF4. Come to next. Here AB3 E2, 3 bond pair are present, 2 lone pair are present. They will be arranged like this. Okay, this is trigonal bipyramidal geometry. But here also you will see that shape and geometry are different. The geometry is trigonal bipyramidal, but if you will cover it, you will be able to see the T shape, so it gives the T shape. Such a shape is shown by CLF3. Such a shape is shown by CLF3. CL being in the center, F making bonds like a T, and there are 2 lone pairs. After that, next 5 bond pair, 1 lone pair. It will be arranged like this. Okay, here also you can see the geometry is octahedral, arrangement is octahedral, but you will cover the lone pair, and what you will be able to see, such a square, but not bipyramidal, only one pyramid, that's why square pyramid. This kind of geometry is shown by BF5. Okay, sorry, BRF5. Okay, last one, see here, AB4E2, it means 4 bond pair, 2 lone pair. They could be arranged like this. Again here the octahedral geometry is here, it means arrangement is like octahedral structure, but since there is a lone pair, there are 2 lone pair. Cover them. When you will cover them, you will be able to see square planar. Okay, you will be able to see square planar shape. Okay, so the shape is square planar, while the arrangement, the geometry is like octahedral. So that's how the presence of lone pair makes a difference in the shape. So in hybridization, we have studied that the shape of a structure can be known. If we know the hybridization, we can find out how many lone pair bond pairs are there, the angle of the molecule, okay, the stable geometry of the molecule, the shape of the molecule. So this is all about hybridization. I hope you like the lecture.